Hi, everyone. It is an honor for us to have the opportunity to speak here. Our topic is a deep dive into privacy dashboard of top Android vendors. First, I want to introduce our team briefly. We are security researcher at IES Red Team of ByteDance, and our research focuses on privacy protection of apps and vendors. We are also interested on application security, including mobile security, web security, and cloud security. This is our presentation outline. First, I will introduce how privacy dashboard works. Then, I will introduce what is Android App.Our. Next, my colleague will show the detail and some flaws of vendors' privacy dashboards and explain our measurement and test method. Finally, we will summarize our research as the conclusion part. Now, let's begin from a privacy dashboard. We will talk about these topics in these sections. Why do we need a privacy dashboard? What capabilities does the privacy dashboard have? What is the basic working mechanism of a privacy dashboard? Although Android introduced runtime permission in API 23, there are still some defects in the permissions management. Once the permissions are guaranteed, they cannot be controlled. Now we come to these questions. After users guarantee those permissions, what can apps do to invade users' privacy? What can operating systems do to protect users' privacy? We have listed 4 categories of applications behaviors. The first one is about data access. For instance, an app can steal the context of the device or read and upload all of the user's photos and videos in the background. Or they can read EXIF data without applying for additional permissions. Secondly, an app may modify the user's state. For example, it can write data into the calendar or clipboard for advertisement purposes. What's more, it can delete the target media files in users' devices. The third one is easy to understand. Some apps can secretly use a camera or microphone to monitor users. Many users have questioned this point in the past time. And the last one, an app can launch itself without users' intention or start the other apps as an alias. Usually, we call them auto start and chain start. It may consume the performance of the user's mobile phone in the background. Let's turn to operating systems. What can operating systems do to protect users? The basic way is to restrict the system functions or APIs. As we know, Android is constantly working hard on this part. But it's not enough. We need some microscope to let users know what apps do. So we need a privacy dashboard. By using a privacy dashboard, it can let users know what apps do. Then they can identify the malicious apps by themselves. Privacy dashboard is a permission record center that allows users to see how apps are setting data. It can have these features. First, a privacy dashboard can show the timeline of certain permissions used by different apps. For example, all of the apps that use camera will be recorded in a dashboard. Android 12 implements a privacy dashboard like this. We will introduce it later. Second, it can monitor sensitive behavior of an app, since users can fully understand what data this app has accessed during the past time. In this picture, we can see that within 1 minute of launching, the application has taken photos, read the clipboard, and then locate the user. There are many privacy dashboards can promote sensitive access in real time. As we can see, if the app reads the context, our system can capture it and promote it on the top of the screen. The latest Android 12 also implements a basic privacy dashboard. It monitors 3 sensitive permissions: location, microphone, and camera. This dashboard can show all of the apps which access these permissions. By using the privacy dashboard of Android 12, we can see the timeline and frequency of these accesses and manage the related permission easily. Here is a diagram that shows how the privacy dashboard works. In a word, the app's action will trigger an operation to note in App.Our. Then, the dashboard reads data from the App.Our server. For example, App A wants to locate this device. When it tries to get latitude and longitude, it will trigger the OP permission Android Find Location for App.Our manager. When users open the privacy dashboard, it will request data from the App.Our manager. In this case, it will request permission group of Android location. Then, it gets the usage data of all apps from this group, including Android Find locations. By viewing App.Our data on a privacy dashboard, users can learn what time does App A get location info, how many times and how long does this app locate the users. As we mentioned above, App.Our is used in privacy dashboard, and it is the most important part in app operation management. In this section, we want to introduce and discuss it under Android open source project, the latest branch of Android 11. Because Android is developing, there may be some variation in detail. Let's come to this topic. What is App.Our? Why do we spend a lot of time analyzing it? Through the research for the privacy protection mechanism from different rooms, we found that App.Our manager is the most important part. Thanks to the openness of Android, we can go deep into it with the help of LSP. As you can see the image on your left, App.Our was added in Android 4.3 API level 18, which is designed for access control and tracking. It identifies an app by UID and package name, then track and record an app's operation. Many people may want to ask, Android already has permission control, such as runtime permissions. We can feel it every day. Why do we need App.Our? In my opinion, first, App.Our added in Android before runtime permissions. I guess maybe Google once thought about replacing permission with it gradually. Second, there are many differences between operations and permissions. One operations can be interpreted as a behavior. For practical reasons, operations and permissions are not one-to-one correspondence. There are 53 permissions in Android systems, but 105 operations in App.Our. There are 52 operations that do not have corresponding permissions, such as write or read to clipboard and so on. But is App.Our completely independent from permissions in Android behavior control? The answer is no. Let's take a look at the workflow behind Android systems. When a system action is triggered, Android uses beginner as the main IPC method. When the system service is invoked by the app, the proxy of the service is usually invoked instead. For example, clipboard manager corresponds to clipboard servers. Wi-Fi Manager corresponds to Wi-Fi Service Implement. Apps.Our Manager corresponds to App.Our servers. During development, an app uses get system servers to get the corresponding manager and indirectly call the API of the corresponding servers. App.Our will be called by service API in the most cases. According to the dimension of usage time, App.Our operation can be divided into two categories, single-time behavior and continuous behavior. For example, reading contact info is a single-time behavior, while using a camera or audio is a continuous behavior. Therefore, for the two types of behaviors, App.Our Manager has Node.op series APIs and Start.op series APIs, which corresponds to Node operations and Start operation series APIs of App.Our servers. In the most cases, system servers will call the former to check and record permissions, but there are exceptions. For example, Activity Manager servers may directly call App.Our servers node operations. So, how can we get the data recorded by App.Our? As the server started with the systems, App.Our implements its own dump method. Therefore, we can use dump App.Our or App.Our dump commands to get App.Our record date. As you can see the image on the right, we can get detailed date of the target API of the target app. As we can see, the dumped date identifies a certain app by package name. In the record of the target app, detail is displayed with OP stream as the basic item, such as camera, read clipboard. In the OP entry, we can see the current setting statutes for this OP, like allow, default, and ignore. Next is the date we are most concerned about, access and reject time, which represent the last time the app tried to access this permission. The following is some other information, including background or foreground, and whether it is an operation performed by a proxy application. For long-term operations, such as camera, it will contain a duration time. Through this information, the sensitive behavior of an app is fully visible to us. But the data from App.Our dump is still not enough. As a security researcher, we are more interested in the reason why the app generates a certain operations. We need to locate the stand code. Android 11 introduced state access auditing, which provides functions to solve these problems. By tracking the code stack in the runtime, it can help developers to locate the code that executes these operations. The official method is to set the OP node callback of App.Our Manager, override the target method such as onNode, and define a method to print code stack such as log private data accesses. The official recommendation is to set this at the beginning of each activity, but through the understanding of the startup process of the Android app, there is an earlier position, attached base context of the applications. If you are an app developer, you can use the above method, but as a security tester, we often encounter apps that have been compiled and packaged. The app release version usually do not use this data access auditing APIs. We provide the following ways to assist security tester to analyze an app. The first method is static injection. For example, we can decompile a target APK to modify the code, inject OP node callback related classes and method, then repackage and sign it. The second method is dynamic injection. We can dynamically inject OP node callback related objects into the app's process. In this way, the sensitive trace information can be obtained from the client side. Of course, we can also do the injection on the server side. We can inject code into system server and hook App.Ops system server node operation APIs to monitor apps OP access operation. Since system server is a system process, this is actually equivalent to indirectly modifying the room. Think about the vendors that can customize rooms based on Android. Do they use App.Ops to monitor privacy behavior? The answer is yes. Next, we will introduce some privacy dashboards, which are implemented by different vendors. Using those dashboards is not only suitable for security testers, but also allows normal users to better understand the sensitive behavior of the applications. I will now hand it off to my partner.
Next, I will introduce our vendor part. We take a deep research on 5 vendors' privacy dashboards and found they are different. They use different technique. First vendor, some vendors extract App.Ops records and show them directly, include the permission state like accept or reject, also access time, background or foreground, and the duration time of obtain sensitive data. Some vendor modified App.Ops source code, for example, add some self-designed opcode to monitor dangerous behavior, and some extra code in node option or node proxy option. Little vendors choose to implement custom dashboard fully, such as empty or temporary privacy data. Besides, some vendors protect albums to avoid the malicious delete. This is an overview of this vendor's dashboard. We classify 4 dimensions from data collection, background behavior, frequency, and other custom protections, include 5 vendors. From table, we can see that most of vendors support basic data monitor like camera, microphone, contacts, but none of them support fully. For example, partially support or inaccurate. So we marked it as TBI. For background behavior and frequency, only little vendor can support well. For some custom functions like album protection, most of them are inaccurate. We will discuss this later. The first case is app get network signal by call get connection info. You can see that the left picture. But vendor sees dashboard will report get location info. We can see the picture on the right. So that's very ridiculous. Network signal has nothing to do with the location. So this is absolutely a false alarm. We take a further analysis on this case, and we extract all the code stack of get connection info. So we found that App.Our will take get connection info as a file location option. So it is the same implementation in AOSP. This monitor strategy is over-designed, we think, because get SSID or get BSSID should be considered as location-related API, but not get RSSI. So we think that vendor should watch the get SSID API, not their further mode, get connection info. This is the first case. The second case is that app release camera normally before they switch into background. We can see the left picture. The app just called camera release. But vendor A dashboard will report in the background take photo or videos. We can see the right pictures. The only reason is that user set navigation method as gesture. We can see the picture in the middle. So when you figure slide from bottom to top and to push your app into background, your app will be reported as background camera obtained. We also use dumsys to extract App.Our logs and found that there is actually a record showed background camera usage. We can see from the picture, the BGS is short for background shelf, and the duration time is 60 milliseconds. So this time is a rare gap, even can't be used to take a photo. So it's very ridiculous. However, vendor A extract App.Our records and show them all the results in dashboard purely, which give a false report. So why gesture navigation led to background camera? We also take a deep analysis. First, we found that Android defined UID state to identify foreground and background. If app didn't release camera before UID state change time, it will be regarded as background obtained. We conducted some tests to calculate the time gap between on-pause and on-UID state change. From the table, we can see that gesture navigation is around 300 milliseconds, but three button is 500 milliseconds. So, for example, if camera release cost 400 milliseconds in the condition of gesture navigation, at that time, UID state become background in 300 milliseconds. So it costs to a background obtain. We think because there is more UI factor in gesture navigation compared with three buttons, so it may cause false alarm about background behaviors. This is the second case. The third case is that app may bypass album protection to delete pictures. When app try to delete a photo, many vendors will prevent the delete option to protect users' album. You can see that the system will pop up an alarm to notify users' app behavior and intercept the files moved to a backup folders. So we can see there are 4 vendors picture, and if the malicious app try to delete photos, so the user will receive a notification about to prevent the delete and move them to a recycle folders. However, vendors take different ways to protect albums. For example, vendor B rewrites the delete function of media provider. But malicious app can delete files with other APIs. For example, java.io.file.delete. Vendor E check DCIM path and hook the delete to identity malicious behavior, but ignore the native delete API, such as libc remove. Vendor A and vendor C monitor kernel unlink. It seems complete for a delete option, but ignore the rename function. So a malicious app can move photo files into other paths, then delete it, so that it bypass vendor's protection. So next, we will describe how to extract App.Our API from Android source code. And we also introduce a solution to extract sensitive API from vendor room. Finally, we will show our tools to test and verify vendors' private dashboard. First, we extract App.Our API from Android source code. We found that most methods use animations to mark the required permission, while some others are declared in code comments. And our methods work as follows. First, we extract all the classes from Android source code and extract all the methods and then construct a triple S signature, comment, and motion for the method. We find that all the methods marked with permissions. Finally, we classify the permission as a key and other methods info as value. In Android, not all sensitive behavior have permissions. For example, the clipboard and the app list have no corresponding permissions, but may be marked as sensitive behaviors by vendors. So we proposed another solution based on the reachability analysis. Our methods work as follows. First, we extract necessary binary files from the vendor's room, such as framework, service, and some custom models. Then we construct the method call graph among them. We can see the left side is the system core of Wi-Fi model, and the right side is the system core of clipboard model. They both finally cause a note option in App.Our service. Finally, we merge the APIs collected by source code and reachability analyze together as our faucet of App.Our API. Build code graph for one model is easy, but cross-model is very difficult. From the code example, we can see that get connection info is invoked from M service, which is actually the binder of iWiFi manager. And the iBinder implementation classes is iBinder.stamp. From the binder mechanism, it is clear that there is a connection between Wi-Fi manager and Wi-Fi service implementation. So we construct a bridge to connect these two objects. In this way, we build a connect code graph across different system models. That's all for sensitive API. Next, we will verify whether this API indeed triggers the vendor's privacy detection. We built a tool called Blue Sandbox to verify our findings. The last image is a preview of this tool, which covers most of sensitive behaviors, including location, device state, and camera. The second two images are the location model and the device status model. From the picture, you can see many related API are flagged, and we also mark the sensitive level with different color. With the help of Blue Sandbox, we succeed to verify 5 vendors' privacy dashboard. Finally, we summarize 3 key points from our research. Privacy dashboard is a new feature on Android 12, aimed to keep track of apps' sensitive behaviors. But several Android vendors achieved their own before. App.Our provide interface to check sensitive permission access, but not accurate or comprehensive for vendors to present on privacy dashboard directly. Vendors' custom privacy protection mechanism need to be improved and need to be verified fully to protect billions of users' privacy. Okay, that's all our presentation, and thank you very much.